as things stand right now, and that may change in the course of this class, you're probably not going to get back your unit exam until tomorrow to take a look at it. Okay? So today we're looking at geometric series that are infinite in nature, and it's more than just saying, well, we have a geometric series that's infinite. There's some property of infinite geometric series that identify some of these series as being what's called convergent and some as being divergent. And that's one of the goals today, is that you're expected to know the difference between what a convergent geometric series is and what a divergent geometric series is. And also, not just to be able to know the difference, but to be able to look at a series and say, that one's divergent, that one's convergent. So you need to understand the general idea of what that means, and you need to be able to specifically apply it to situations. And then we're going to be solving problems involving convergent geometric series. We can't solve problems involving divergent, because the problems are not solvable. And we'll see why in a little bit. To begin with, we're going to, as a warm-up, compare two different geometric series. The first one is, I'm labeling it as number 1. It's 2 plus 1 plus 1/2. Don't forget, a series means we're adding things together. Okay? And it continues in that fashion. And the second series is 2 plus 4 plus 8. And it's probably not that difficult for us to figure out what the common ratio is. I know you've been away for a few days. But the common ratio is what you multiply one term by to move forward. So when we take a look at the second series, it's easier for us to see and explain the second one. 2 gets multiplied by 2 to get 4. 4 gets multiplied by 2 to get 8, and it continues in that manner. What that means is that the common ratio here is 2, and we can make an observation by either writing it down or just looking at it and knowing that it's 2. And on the other hand, this geometric series has a common ratio of, I'm in a decimally kind of mood this afternoon. Let's just go 0.5. We could write 1 over 2, that's fine, but the common ratio is 0.5. And I want to warn you here, because there's some ins and outs of this that can get a little tricky. Try not to get too far ahead of me on this. What we're asked to do is complete the table for the following series. So we want to know what S4 is and S5 is. And the reason why I said don't get too far ahead of me is I looked out and I saw people already clicking away on their calculator. And we could certainly do it that way. But by the time we get to S10, that means we're going to have to write out the 10 terms and then add them together. And I'm going to make a suggestion, which is that we don't need to do that. We can use the general formula for the sum of n terms of a geometric sequence, or series rather. Now, you might want to have your formula sheet out in front of you for today's lesson. I think this is T1 times r to the n minus 1 over r minus 1. Am I right there? I am. Okay. I thought I was, but you know how it goes. Sometimes you're not sure. So what I can do is I can put in the parameters for this series. The parameters are T1 equals 1 and r equals 0.5. And one of the reasons why I said I'm feeling decimally is I think it's going to be easier to use the decimal. Yeah. What did I just write? Oh, really? T1 is 2. Thank you. T1 is 2. The first term is 2, and the common ratio is 0.5. Those are the parameters that define the series. So I'm going to load them into that general formula and get S sub n equals the first term, which is 2, times 0.5 raised to the n minus 1 over 0.5 minus 1. And I'm going to just abbreviate that denominator a little bit. I don't feel as though I need to write 0.5 minus 1. 0.5 minus 1 is negative 0.5, I think. Give that some thought. So what this becomes is 2 times 0.5 to the n, then minus 1, over negative 0.5. And I can simplify that more. Because the 2 is in brackets multiplying across the top, I can take that 2 and divide it by negative 0.5 and condense those two numbers. And you're going to do the same on your calculator here. You're going to take 2 divided by negative 0.5 and see that you get negative 4. Am I right, or am I out in left field here? 2 divided by negative 0.5 is negative 4. So what we have now is S sub n equals negative 4 times 0.5 to the n minus 1. And we could end there. I'm going to go one step further. We could multiply that negative 4 in. And if you think carefully about what happens, this 0.5 to the n is positive 0.5 raised to the n. If I multiply it by negative 4, I'm going to get negative 4 times 0.5 to the n. And when I multiply the negative 4 by the 1, I get 4. So this is what we can use to find the sum. Now, I just want to be careful here. Make sure you understand. You didn't need to simplify any of this. Okay? You didn't. To fill in this table, you didn't need to do so. I chose to do so, though, because I want to put this in for y1 so I can generate this table. And I would rather put something in for y1 that's simpler than a big mess. So I'm going to put that in for y1 in my calculator. And then we'll populate the table, but I really want to slow down here and make sure you understand what's going on. So we go to y equals, clear that out, it's 4 minus 4 times in brackets 0.5, close brackets raised to the x. Of course, we have to use x. We don't have an n. What does this mean? Okay. Well, without using the calculator, I hope you can see that S1 is 2. I don't have 1 on my table, right? But would you agree, looking at this series, S1 is 2? Would you agree S2 is 3? S3 is 3.5? Okay. So if I go to my table setup and I start at 0 and go up by 1, and I look in my table, it's giving me, I want to start at 1 rather, it's giving me the sums. This number here is the sum of the first term. The second number is the sum of the first 2 terms. Then it's the sum of the first 3. And we're going to be looking at these numbers anyway, so that's why I want them accessible on the calculator. The bottom line is we can take these numbers, and I'm just going to have to copy this because I can't look at both my calculator and the notebook software at the same time. Well, I can, but I would have to resize things. That S4 is 3.75. S5 is 3.875. Then 3.9375, 3.968. By the way, I suspect that S7 is not 3.9688. I suspect it's 3.96875. And if you want to see the details of these numbers, you can scroll down and highlight it, and you'll see that there are other decimals that we're not seeing. And I want to go up to 9, I believe. No, I would like to go up to 10, so I'll grab this again. S8 is 3.9844, and I probably 9843125, or who knows what it is. It's weird decimals. And 3.9922. And then 3.9961. I'd like to point out to everybody that the sum keeps, missing a decimal there, the sum keeps getting bigger. Yes? And that makes sense because all of these numbers are positive. Every time you add another one on, you get more. All right. Let's take a minute and do the same thing for the second sequence. What would our general formula be? Well, it would be Sn is the first term, which is 2. Let me write down my parameters here again. T1 equals 2. R is equal to 2. So I would get 2 times 2 to the n minus 1 over 2 minus 1. Just take a minute and roll that around upstairs and make sure that that makes sense. I think it's fine. On the bottom, on the denominator, it's 2 minus 1, which is simply 1. So Sn equals 2 times in brackets 2 to the n minus 1. I don't feel the need to multiply that 2 through this time, because the reason I did it with the negative 4 is if I had negative 4 outside, then I also had a negative inside. When I multiplied the negative 4 through, I ended up with fewer negatives. That's really the reason why I did it. So we can do this. On the calculator, 2 bracket 2 raised to the n minus 1. Close brackets and get rid of everything else. I guess let's start at 4 and go up by 1, because that's what we want to know here. Would everybody agree, looking at the screen, that the fourth term is 16? 2, 4, 8, 16 is the fourth term. Can you please add up 2 plus 4 plus 8 plus 16? Figure out what 2 plus 4 plus 8 plus 16 is. You get 30, don't you? Okay, well that's why S4 is 30. My table is showing me all of the sums. So S4 is 30, then 62, 126, 254, 510, 1022, and 2046. And the specific numbers we're getting are not important. Before I get back to the lesson, the formal part of the lesson, I want you to take a look at both of these tables. I'm going to put them both up here so I can see them at the same time. So there's the second one on the right-hand screen, and here's the first one on the left-hand screen. And we made an observation that the sum for the first series that has a common ratio of 0.5 was getting bigger. It's getting bigger, isn't it? And when you take a look at the sum for the second series, which is on the right-hand screen, and you can't see it in the video right now, but it's on the right-hand screen, the sum is getting bigger. Thank you for that, Nate. $1022, not 10,222. When we take a look at both of these, each of them has a sum that's getting bigger. But I hope you can see there's a different way in which the first series is growing compared to the way in which the second series is growing. It's a difficult thing to put into words. But that being said, does anybody want to give it a crack? They're both increasing. The sums are getting larger and larger, but one of them is increasing in a different way than the other. Aoki.
The one on the left is increasing in a smaller amount each time.
Perfect. That's a great observation that the one on the left, which is the one we're looking at right now on the video, Series 1, is increasing each time, but it's increasing by a smaller amount. Why is that?
Because the terms in the series are getting smaller the further you go.
And why is that? Why are the terms getting smaller?
Because the ratio is cutting them in half.
Right, the ratio is a small number. Specifically, it's less than 1. So we're adding a number each time that's getting smaller and smaller and smaller. Whereas this particular series, since the common ratio is a number bigger than 1, what we're adding each time is a number that's bigger than the last number we added. So when we find S10, we're adding T10, which is even bigger than T9 was. And then when we find S11, we'll be adding T11, which is even bigger. But now comes the interesting part. This series that you're looking at here, series 2, is getting bigger and bigger and bigger, yes? Will it continue to get bigger without boundaries? In other words, will it eventually pass 10 gajillion? Yes. And that kind of makes sense. If something is growing, it's going to continue to grow. Will this series have a sum which continues to grow without any limit or boundary? Keeps getting bigger. Will it reach 10 gajillion? We keep adding more and more and more to it. Well, now we can go to our calculator and I want to go, though, in my calculator back to the original one where I had, it was 4 minus 4 times in brackets 0.5 n bracket raised to the x. Can you confirm that was series 1? Okay, good. I want to go to my table, but I don't want to leave my cursor there. I want to put it over here in the y column. And I'm going to scroll down. I'm going to keep my eye on the number at the bottom of my calculator screen. Now it went to 4 there. But the reason it went to 4 is there's so many 9s following the 3 that my calculator just kind of shrugs and gives up and says, I'm going to tell the user that it's 4. And I can prove to you with a thought experiment that this can never reach 4. This sum will never reach 4. I would like you to imagine that I have a distance of 4 meters from one point to another. And I'm going to start here on the left. And I'm going to imagine that I'm standing at that point on the left and I'm going to walk 2 meters. Well, that would be exactly half. Let me get my ruler out. It doesn't have to be perfect, but I do want a decent job done. What am I looking at here? 21.7. What's half of 21.7? 10.525. 21.7. No. 10.85. 10.85. So the middle of this is about here. Don't know why it does that. That's okay. The middle of it is about here. And what I have done is I've walked 2 meters. And now I am here. Right? I'm going to now walk half of the remaining distance. So I'm still 2 meters away from the wall. I'm going to walk half of the remaining distance, which puts me here. And that is 1 meter. I'm now 1 meter away from the wall, or that right-hand point. I'm going to walk half of that distance, which will put me here. And I will have walked another half of a meter. I hope you see that as long as I use the rule that I'm going to only walk half of the remaining distance, I will never hit that last point, will I? And in theory, I could do this an infinite number of times. And what that means, I'm going to get rid of the m's so we can just talk about the pure numbers. What that means is this will never reach 4. It'll get closer and closer and closer to 4. Now comes the part of math that people don't really like to think about. How many steps would I have to take in order to reach the wall? See, I can see some of your brains are just, you got this kind of giggle look on your face because you don't know exactly how to answer that question. There's an answer to the question. It's just not an answer we like to talk about very much until we get to this level.
Like an infinite.
It is an infinite number of times. And that ellipsis that I've drawn, that dot, 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 that means forever. So this sum is going to be 4. When we talk about the sum of all of the terms, of the infinite number of terms, it's going to be 4. Keep that in mind as we work through the rest of this. Okay, what happens to the sum of the terms in each of the two series as n approaches infinity? Well, let's talk about series 2. As n, the number of terms we're adding, approaches infinity, the sum of those terms will also approach infinity. You look at that table, was it 1024 and then 2044 or whatever the numbers were? They keep getting bigger and bigger and bigger. I guess it was 2046. Thank you. They just keep getting bigger and bigger. The idea here on the left, though, is as the number of terms approaches infinity that we're adding together, the sum of those terms approaches 4. Which means, and this again, you got to kind of break your way of thinking here about numbers and what infinity is. Because I was always taught you can't reach infinity, and that's true. I remember an elementary teacher telling me, if you think you're at infinity, add a number to that, and you're clearly not at infinity. You can keep going. But the concept of infinity is very important in mathematics, and what we would do here is say that the sum of the infinite number of terms is 4, because if you could add an infinite number of terms, you would reach 4. But you can't, but we call the sum 4 anyway. Geometric series that are infinite in nature, that go on forever without boundary, and both series 1 and series 2 are infinite. They have that ellipsis, that dot, dot, dot. They can either be convergent or divergent. And a convergent series is a series, it's geometric, is a series that has a sum which approaches a value. That's an example that's illustrated best with series 1. That sum was approaching 4. And the word convergent is used because converge means to approach. I just saw somebody do this. It's exactly what converge means. If you have lanes on the highway that are converging, they're coming together. So what we have, and you can choose to add this wherever you like, if you like. What you have with convergent is if you have a graph of Sn as a function of n, it doesn't matter what the sum is is going to get bigger and bigger and bigger and bigger and bigger and bigger, but it's going to approach some value. And it will never reach that value. The sum is converging on that value. So in our example, this was the number 4. And it went from 2 to 3 to 3.5 to 3.75 to 3.875. I can't remember the numbers, but it was approaching that number of 4. And we will learn in this course later on that on a graph, when you have a dotted line, might as well throw this word at you right now. This is called an asymptote. It's one of the goofiest spelled words in the universe. It's just a line that the graph will never reach, but it will always get closer and closer to it. So this demonstrates that the sum is converging on that value. It's getting closer to it. With a divergent series is like series 2 in that the sum keeps getting bigger and bigger and bigger. It's diverging away from 0. It's just approaching infinity. So I'm going to draw that right now, and then we can get back to the notes in a second. But if you had a divergent and put as many dots in here as you like, but this thing just keeps going. And I'm going to actually draw what I just looked down. I just saw somebody else draw, but I'm only drawing it for the purpose of explaining. You should understand that these graphs are discrete. These data points should not be connected. Okay? But, yes, this curve demonstrates the pattern, and this curve demonstrates the pattern that we're talking about here. But really, it's only the dots, right? You can't have a 1 plus 1.5th term. Do you know what I mean by that? You can't have a term in between the first term and the second term. So you can't have a sum of 1.5 terms. Okay, so what is divergent? Series has no sum that is approached. In other words, the sum just keeps getting bigger and bigger and bigger. Doesn't matter how many terms you add, it just keeps exploding, larger and larger and larger and larger. All right. And this is perhaps, this lesson is the only lesson in the unit that really is about thinking. It's not just about formulas, although there will be a formula. It's about thinking. All right. The first term of a geometric series is 3, and the common ratio is -1/5. Does the series converge or diverge? That's the question. And in order for us to see if it converges or diverges, we have to look at what's happening to the sum. We have to find S1 and S2 and S3 and S4 and ask ourselves, is it exploding or is it settling down to some value? So we're going to generate a table again. Let's write out the parameters of this series. T1 is 3 and R is negative. I'm going to go with decimals just because it's easier to do the work on the calculator with decimals. I think -1/5 is -0.2. Okay. So here's our sum formula for any geometric series. T1 times R to the n minus 1 over R minus 1. If I put in the parameters, Sn equals 3 times, we do need brackets around this common ratio this time because it's negative. Can we please calculate the following? What is 3 divided by this? It would be nice to take those numbers and condense them down to a single number, and what I'm thinking is it's -2. -2.5? My mistake. So I can write this as S sub n equals -2.5 times, in brackets, -0.2 raised to the n minus 1. I know I made a big deal of multiplying that negative through earlier. I don't want to touch that here because I've got embedded brackets, and I don't want you to perhaps think that some negatives go away. We're going to enter that into our calculator. for y1. Of course, we don't have n, we're using x, so I'm going to put negative 2.5 times in brackets, another set of brackets, negative 0.2, close the brackets on the r, raise that to the x, then minus 1, then close the brackets on the whole deal. And I want to start at S1. Okay. In fact, you know what, before I do, is this the first term? Can you confirm that the next term is negative 0.6? I'm not talking a sum. I'm just saying if we take 3 times the common ratio, we get negative 0.6. And can we confirm that the next term is positive 0.1812? Okay. So this is what we're talking about. We're having these sums that we're adding. And the next one would be negative 0.024. I don't know. I'm not talking a sum. I'm just saying if I multiply 0.12 by negative 0.2, do I get negative 0.024? Okay. Before we get to the calculator, I want you to notice that we're starting at 3, and we're going to add a negative number, and the sum is going to be less than 3. And then we're going to add a positive number, and it's going to go up. And then we're going to add a negative, and it's going to go down. So it's going to be wobbling. It's not going to be going up or down. It's going to be doing both in a one after the other fashion for the sum. So when I take a look at the sum, I want to start at 1 this time and go up by 1. The sum goes from 3 to 2.4 to 2.5 to 2.496 to 2.5. Does it reach 2.5? Doesn't look like it. And what's happening here, I want to show this to you graphically in the same way we talked about what was going on before. There is going to be a value at 2.5, and when we add the sums, this is what happens. Every time we add the next number, it flips to the other side of 2.5, but it gets closer to 2.5 than it was the last time it was there. So if I go back and look at this graph, I drew this to show you that the dots converge on that horizontal asymptote, but it doesn't matter. It could converge this way. It could go above and below and above and below, but it just keeps getting closer each time. And again, we're at the mercy of your calculator here, that if you continue to scroll down, my calculator is eventually going to shrug and go, let's just call it 2.5. But it's not 2.5. If we put this formula into Excel and told it to record and report the answers to 1,000 decimal places, we would see that it never reaches 2.5. And, you know, I'll be the first to admit that this is a very clunky way to determine that this is convergent. It's very clunky because you don't want to have to do what we just did in the calculator every time to decide that. Are you with me on that? Okay. So this is convergent. By the way, the sum is equal to 2.5. And we could say S infinity if we liked, if we wanted to. All right. Well, if it is convergent, and this is tricky, this is the final formula in this unit. If you know that a geometric series is convergent, then you can find the sum using this formula. Notice there's no subscript on the S. It's not Sn. What this means is S infinity. So, for example, in the previous example, we decided this was convergent by looking at the pattern of the sums. And it had a first term of 3 and a common ratio of negative 0.2. Go ahead and work this out. Go ahead and take 3 divided by whatever 1 minus negative 0.2 is. 2.5. Okay, before we go on, and there's more to this, I'm going to take this formula and let's use the formula here. Let's not write anything down though. I'm going to use this formula. Is this an infinite geometric series? Is it infinite? Is it geometric? Yeah. So let's try this. And again, you're not writing this down because it's wrong. S equals T1 over 1 minus R. Would you agree that if I put T1 in and R in, I get 2 over 1 minus 2? 1 minus 2 is negative 1. 2 divided by negative 1 is negative 2. That's clearly not the sum of the infinite series, right? Why? What, have I done something wrong here? I must have. What did I do wrong?
You used the formula for divergence.
Perfect. I used a formula that's only useful if it's convergent, and I used the formula for a divergent. The point I want to make to you is this statement here, or this phrase here, is crucial. We're talking about, and I have to wait for my computer to unlock, we're talking about here only if it's convergent. Only if it's convergent. Okay. So, can we use the formula here? This is what this question is asking. Wow. Yes or no? That's a new one. I've never seen that before. Yes or no, are we allowed to? Well, you have to decide whether it's convergent. And now comes the part of the lesson where I haven't let the cat out of the bag, so to speak. There's a rule that we're going to use here, but how many of you see that this will be convergent? What is it about this, you think, Ashira, that is saying it's convergent?
If the common ratio is less than 1.
Right. So if the common ratio is less than 1, then each successive term is smaller and smaller, and that means you're going to be adding something, which means the sum is going to grow, but you're adding something smaller and smaller each time, which means it's growing by a smaller and smaller amount. And this will be convergent. And if you wanted to, you could go to your calculator and confirm it. But because it's convergent, and I'll give you the rule officially in a second for the convergency in terms of the ratio, yes, we can use this formula. So the sum of the infinite number of terms will be 10 over 1 minus whatever the common ratio is. So there's a little bit of work here. T2 over T1 would be the common ratio, so that's 2 over 10. How many of you can just look at that and say it's 0.2? Okay, so the common ratio is 0.2. And we can work out what that is. I want to say 12.5. Is that right? And this goes way back to the beginning, which is when I saw people putting in their calculator 2 plus 1 plus 0.5. You don't need to do that at all. Well, this is going to be divergent. I think it's pretty obvious that the numbers are getting larger, so you keep adding more and more. And not only are you adding more, you're adding bigger mores. You're adding numbers that are even bigger. So this will be divergent. Which means no sum exists. I mean, you can find S10, you can find S a million, but there's no S of the entire infinite series. Now, earlier when I asked how we knew that this one was convergent, Ashira answered because the common ratio is less than 1. But there's more conditions to it than that. For example, the common ratio can't be 0. By the way, if the common ratio is 0, the sum will exist, because all the terms reduce to 0 right away, other than the first term. But that's a trivial example. You could even convince yourself that if the common ratio is 0, this formula works. Because if the common ratio is 0, the bottom of this becomes 1, and then you're saying the sum of the infinite number of terms is the first term, which it would be. It'd be the first term plus nothing, plus nothing, plus nothing. But that's no longer geometric. Geometric sequences and series cannot have 0 ratios. We did see, however, I just want to go back and show it to you, in this example, that this had a negative common ratio, and it was convergent. So the bottom line is it has to be a number that's smaller than 1, bigger than negative 1, but not equal to 0. What this says, and you can feel free to add a number line if you like, is that if you look at a number line where this is negative 1, this is 0, and this is 1, the values of R that are permitted for it to be convergent are described by that green diagram. Anything between 0 and 1 or between negative 1 and 0 makes it convergent. So what I've got here, clean this up just a little bit. What I have here is saying the same thing as what I have there. And you know, there was a time in my teaching career where I would have just started off with this and had a 5-minute lesson, but I think you learn a lot about infinity in going through and looking at these sums, because ultimately you have to be able to solve. So there's the summary, right? If that's the case for R, it's convergent. If it's convergent, you can use that formula. You can do these problems now. Determine if each infinite series exists as a sum. Well, first of all, is this convergent or divergent? Nate? Why is it convergent? Right. When you say it, you mean the common ratio. The common ratio is negative 1/3, which is between negative 1 and 0, and it's not equal to 0. Sorry, negative 1 and 1, and it's not equal to 0. So we can use this formula. First term over 1 minus R. And I'll give you a second to crunch those numbers. $3.75. if I were you, I wouldn't, I mean, you can feel free to use brackets. I would just calculate the bottom and then take 5 divided by my answer. Determine the sum of this. Does the sum of this infinite series exist? No. If I had to press you and say, no, tell me what the sum is, the answer would be infinity. And even then it gets tricky because if the common ratio is negative, maybe it's negative infinity, and that opens up a whole big can of worms. But the bottom line here is when we take a look at r equals 0, r equals -1, r equals +1, 3/2 is over here. I didn't draw this to scale. 3/2 would be maybe there. But that's outside of the domain of values for r that make it convergent. So no sum. And that's it. The types of questions you would see on a unit exam, the ones that I scrapped from that last unit exam because we hadn't learned this yet, would be, giving you different examples of series, whether I tell them to you with T1 and R, or I write out the first few terms, and you being able to identify which ones are convergent, which ones are divergent. Or problems where you have to find a sum. Or problems where I give you a sum and a common ratio, and maybe you have to find the first term. In other words, everybody, this formula, sometimes you have to find this. Sometimes in a problem, you have to find this. Sometimes in a problem, you have to find this. It depends on the situation. Got lots of time today. I want to get you started on this. I would really like to hand back your exams today, but I have to check on something.